So in this video, I'm going to talk about the last part for the inverse Laplace transform. It's part 3. Okay, so a very brief recap of what we talked about in the previous 2 videos. So the inverse Laplace transform talks about how do I compute the inverse. Let's see if I give you a function in the S domain. Suppose that it can be written as fs over gs. So both f and gs, they are polynomials of the variable s. And our goal is trying to figure out what is the inverse of ys. In other words, I want to find the y sub t in the time domain, such that you can also view this as the Laplace transform of yt is ys. So that's equivalent. Alright, so according to the location of the poles of ys, okay, the poles are actually defined by letting the denominator of ys, which is gs, you let it be 0, and you can find the solution to the gs of equal to 0. The solution, according to the location of the poles, we actually talk about 2 different cases in the previous 2 videos. The first one is when ys has real and distinct poles, meaning that the solution to gs being 0 is something like s is 1, s is -1, s is 2, so on and so forth. So we don't have repeated poles, and all the poles are real. That's for the first case. For the second case is when we have a complex conjugated poles. For example, I have s is 1 plus or minus I. So that's called a complex conjugate poles. Okay. So I'll talk about how we can find the inverse Laplace transform for the first 2 cases. Now today I'm going to talk about the last case when we have repeated poles. Here we'll assume the poles are real. Okay, so for complex poles with repeated poles, typically we don't know how to find out this one directly. Okay, so I just focus on the real poles when we have repeated poles. Alright, so we start with the same one. Okay, to give an example about when we have repeated poles. For example, if I give you the y sub s, which is given by s squared plus 2s plus 3 divided by s plus 1 to the cube. Okay, so you can sort of view the s squared plus 2s plus 3 as fs, which is the numerator, and s plus 1 to the cube is called denominator, which is gs. To calculate the poles, we just set this denominator to be 0. Okay, then we find a solution, and fairly easy to figure out. So we have 3 poles, which are -1, -1, -1. So they're repeated because they are the same. We have 3 repeated poles. So the partial fractional expansion or partial fractional decomposition says I can decouple my ys into this form. Okay, which says my ys can be written as a1 divided by s plus 1, a2 divided by s plus 1 squared, plus a3 divided by s plus 1 divided by s plus 1 to the cube. So in other words, for a general case, we can have ys is given, assuming, okay, this general case, assuming the poles are lambda. Okay, so and we have n of this lambda, n of this pose being lambda. Now the general case is ys can be decoupled as a1 divided by s plus lambda plus a2 divided by s plus lambda squared plus so on and so forth until an to the s plus lambda n to the nth power. Okay, so n is the number of repeated poles. You sort of can see the structure of the decoupled form of ys. So also I want to emphasize over here is the degree of fs should be less than degree of gs as well. Okay, you have to make sure this is valid. Okay, now it comes question, since we already know the form already is given by this, so what we need to do is try to figure out those parameters a1, a2, and a3. So that's the main problem we have to figure out. So I'm going to talk about 2 approaches. You can find the coefficients a1, a2, and a3. Of course, in the general case, I want to find a1, a2, until an. You can use a similar approach. Okay, the first approach is called a direct approach. Okay, as I mentioned before, direct approach is just assuming that you have some parameters a1, a2, a3, satisfy this form given by this form, such that this one, the sum of the three will be equal to the original one. That's the direct approach, okay, which means I assume a1 divided by s1, s plus 1, plus a2 divided by s plus 1 squared, plus a3 divided by s plus 3 plus 1 to the cube, which is equal to my y sub s. Okay, now I just reverse to try to figure out what are a1 and a2 and a3 will satisfy this equality. Okay, that's called direct approach. To find out the solution, we just do multiply both sides by s plus 1 and to the cube. Okay, we want to cancel out the denominator basically. Okay, so this way I can simplify. Once you do the product, I just do product to each components. Okay, so we have a1 plus s1 plus 1 squared, because this cube and s plus 1 will cancel out one of them. Similarly, we have a2 plus times s plus 1 and a3. This is for the left hand side when we do the multiplication. Right hand side, this just cancel out. So it just become s squared plus 2s plus 3. Okay, so we just do the calculation of s plus 1 squared here. Okay, s plus 1 we just write it out directly, separate them. And then we just, for this one, the right hand side to be the same. And for the left hand side, we just try to figure out the coefficients for s squared, for s and a constant. Okay, because that will correspond to the 3 on the right hand side. All we have to do next is try to figure out to make sure the coefficients for s squared on both sides are equal. The coefficients for both sides of s will be equal, and our constant will be equal. So we just set a1 to be 1, okay, because that's the coefficient. You can see this is 1 times s squared. And 2a1 plus a2, this one has to be equal to 2, okay. And this guy constant will be equal to 3. Now they are equivalent, okay. Once we do that, we can a1 just equal to 1, okay. We plug in a1 into the second equality, we get a2 is 0. When we plug in a1 and a2 into the last equality, we got a3 is 2. Okay, in other words, we just get s squared plus 2s plus 3 divided by s plus 1 cubed. The original y sub s is the original y sub s. It's just given by this. It's just the sum of the 3. Okay, fairly simple one. The reason we write this one into the 3 component, because I can easily figure out the inverse Laplace transform for each component. Now here we use the linear property, of inverse Laplace transform. So which means the inverse of a ys is the inverse of the 3 individual components, and with the sum, of course. So the inverse of this guy is equal to inverse of the first one, inverse the second one, inverse third one. So the second one we don't care because this is just 0, right? It doesn't have anything. So the inverse of the first one, this is basically given by e minus t. Okay, it's fairly easy to figure out. Is e minus t. As a matter of fact, you can also find a table. So I'm going to show you the table that you can use. So if you want to figure out generally, you can find a table from here. So this table I already talked about is sort of the properties that I mentioned for the Laplace transform. Okay, and also it talks about some basic functions and what's the inverse Laplace transform. For example, step function over here, delayed step function, unit function, and ramp function, and nth power, so on and so forth. You can find all the table, all the stuff over here. This is very commonly used, very commonly used function. We can find its Laplace transform or inverse Laplace transform. For example, I can say the inverse Laplace transform, this guy is just t. The inverse Laplace, this guy is equal to this, so on and so forth. So we can pretty much use this one when we try to figure out the individual one. Let me go back to the original slides. Okay, so individual one. So for this one, for each individual, we can use a table. Okay, so to show you how we use a table, actually I'm going to show you for the first one. If I go back to the table over here, so s plus 1, basically have s plus 1. I'm going to show you where it is. So this is s plus alpha. Okay, so it's just e minus alpha t. So for this case, I'm going to have here is, let's see, so it's 1 over s plus 1. So you have alpha is negative 1 basically. So you have e minus t. For this guy, the last one, I'm going to copy one of this one over here. It says t to the n and e to the minus alpha t times this. You can sort of ignore this. The Laplace transform of this guy is basically t to the n e minus alpha t is equal to sort of n squared factorial s plus alpha n plus 1. In other words, we are equivalent, you can say L inverse of n factorial s plus alpha and to the n plus 1 is just equal to t to the n e minus alpha t. Okay, it's equivalent. So if you look at this one, so you can sort of figure out how to do it. So you can, if you do this one, you can also consider here alpha to be to match this guy matched here. You sort of consider alpha is equal to 1, right? So I have here alpha is 1, and n, because I have 2 to the cube, so n is, because n plus 1, so n is here is 2. So here is 2. So 2 factorial is exactly 2. So 2 factorial is that 2 times 1. So it's 2. So exactly this is 2. This is 2 factor. This is 2, and this is just exactly s plus 1 to the cube. It's exactly this. So we have n is 2. So that's t squared, and minus alpha is 1. So minus alpha t. That's why it's the inverse Laplace is t squared times e minus t. All right. That's why we find the inverse Laplace transform for the ys with repeated real poles. Okay. So this first way we can find the coefficient a1, a2, a3. Another approach you can try is called indirect approach. Okay. I'm going to go over this approach. Okay, so this indirect approach is trying to simplify a little bit in terms of computation, especially we have multiple repeated poles. So here's the basic idea how this works. So you normally start with the highest order you have. So we start with a cubed, okay, a3. So when you do this one, you time both sides by s plus 1 to the cube. This is pretty much the same as I showed over here, okay. Now the next step will be a little bit different. I time both sides by s plus 1 to the cube. Now what I'm going to do is I'm going to set s to be negative equal to 1. Once I do the product, I set s to be equal to negative 1. The reason I'm doing that is because if you solve the first two, the first product a1 divided by s plus 1 times s1 to the cube, you get, because this guy cancels out, you get a squared, basically. This guy cancels out to get a 1, right? Because if I let s be equal to negative 1, so s plus 1 is 0, basically. So this will be 0, this will be 0, so this 2 will be gone. So you only have a3 on the left-hand side, which means I only have to evaluate the right-hand side by letting s be negative 1. So I let this guy and let s equal to 1, s equal to negative 1, so I get negative 1 squared plus 2 times negative 1. I just plug this value into this each component of s. So I get s, a3 is 2. Alright, so once I get this one, so I'm going to go over to the reverse order. Let's figure out what is a2. By doing that, I'm not going to time s plus 1 to the cube. I'm going to multiply both sides by s plus 1 times s squared. Let's see what's going to happen. Okay, this one won't work. I'm showing you this one won't work. If I'm going to time s plus 1 to the cube, to the squared, okay, on both sides, and I'm having here is, you time each component. I have a1 divided by s plus 1 times s plus 1 squared. Of course, this will cancel out. You have just 1 over here. You have a2, and then this guy cancels out. You have here is 1, basically. Now, we cannot set this s equal to negative 1 because this guy will be infinity and this guy infinity. I don't know. I cannot figure out what is a2. Okay, although this is still 0, but this one is a2 plus infinity equal to infinity. I don't know what a2 should be. Okay, this is not working. Okay. Now the correct way I can figure a2 is by doing this. Okay, we still multiply both sides by s plus 1 to the cube. Okay, keeps the cube. Okay. Now I'm going to do a product. If I do a product on both sides, so I have here is a1 divided by s plus 1 times s plus 1 cubed. Then the cube will cancel out one of this. So I have a1 times s plus 1 to the squared plus a2 times s plus 1, because this squared and the cube will cancel out the square. Then it will remain 1 s plus 1. And a3 will be here. And right hand side of the denominator will be cancelled out. So you have s squared plus 2s plus 3. The key concept or key idea is I want to take a derivative of this both sides with respect to s before I want to set a special value for s. Okay, so I'm going to take a derivative of both sides. Okay, to take a derivative, first one is I get a1 times 2 plus s plus 1. Okay, plus a2. Now you just do the s plus 1 derivative with respect to s is just 1. So I have a2. This derivative is just giving us 0. Okay, now I'm going to, of course you can do the same thing on the right hand side. Now I'm going to set up the s equal to negative 1. The reason I'm doing this is because this will be gone because s plus 1 is 0. and only left is a2. Okay, so you just evaluate the derivative on the right hand side and set to be 0 to be s equal to negative 1. The left hand side is a2, and the right hand side is 2 times negative 1. Now you have s is negative 1, right? And replace s by negative 1. Now this, and then the 2 will remain to be here, so the sign will be 0, so a2 will be 0. The same concept can be applied to a1. Okay, you can still apply s plus 1 to the cube on both sides, multiply both sides by s plus 1 to the cube. Now we have to take a derivative of both sides with respect to s twice, and then set s to be negative 1. So you can sort of imagine why that's the case. Now let me show you how we do that. So we, on the left hand side, let me go to take a derivative. Let's clear a little bit again, and then we take this is also left hand side, right hand side, and then take a derivative once. Okay, we get this. Okay, then we take a derivative again. Okay, we get this, right? Okay, we take a derivative again, because derivative here is, if you take a derivative over here, the derivative of this with respect to s is, because this is constant, so this will be gone. And this guy, the derivative of this guy will be just 2 times a1. Okay, and right hand side derivative just be 2. Okay, and if that is equal to next one, you don't actually care about this, right? Because this is 2 times a1 and 2, so I get an a1 is 1, which means I get an a1 is 1, a2 is 0, and a3 is where's my a3? A3 is here. Is go back. A3 here is pointer 2. If you go positive 2, so go back to over here. What I have over here is also 0, 1, 0, 2. Basically, you get the same thing, right? This is 2 a3, and this is 0, and this is 1. So it's the same thing. Okay. So here's a basic basic conclusion or basic concept you can use. If here's for the general case, when I have y-f is given by f is given s, g sub s, you sort of can see you want to. Okay, let me go back to this question first before I go to the general case for the indirect case. Okay, so for what if my y-s has repeated poles and also has distinct poles and also has complex conjugate poles? What's going to happen? Okay. Okay, so I'll show you how we can do it. Okay. So if I have, for example, if I give a y-s which is s cubed plus 3s squared plus 5s plus 6 divided by this whole bunch of stuff. So if I check the poles, okay, suppose I set the denominator to be 0, basically set the denominator to be 0, so you can find the poles are s is negative 2, s is negative 1, negative 1, negative 1, and s is, this is, I believe it's negative 1 plus or minus 2i, so that's a pole. So this is real distinct, because it's different from anyone else. So this is a real repeated. This is complex conjugate. So we have 3 different cases I mentioned it previously. Now how I want to address those? You can sort of mix the 3 different cases I mentioned before to address the issue. You sort of see this can be decoupled as, for the real distinct poles, you follow what is case 1, which means I have a divided by s plus 2 because I only have one of this. You could have more. If you add one more over here, say s plus 3, for example, just here is you get a1 and plus a2 s plus 3. So it's same thing, okay? Then here the second one, you have repeated poles. You have b1 divided by s plus 1 plus b2 s plus 1 squared plus b3 s plus 1 cubed. Okay, because that's for this is for real distinct poles. This is for real and repeated poles, and this is for complex conjugated poles. Okay, so this is for the last one. You just use s squared plus 2 s plus 5. This is c1 s plus c2. Okay, this is for the 3 different cases. And for a, find the pole, find the values over here. Okay, it's just where you can use the one for the case 1. Okay, it's y(s) times s plus 1, and you evaluate as s equals negative 1. You're done. Okay, for the repeated real and repeated poles, okay, you follow the steps. This is the step. This general case I mentioned over here. I didn't mention the general case. Now this is general case how you solve the values. For B3, you just do y(s) times s plus 1 to the cube, and then evaluate s equal to negative 1. For B2, you do y(s) times s plus 1 to the cube again, but you take a derivative and you set s equal to negative 1. So for this one, you actually there's a 1 divided by 1 factorial. Okay, it's somewhere over here. So for b1 is 1 over 2 factorial times ys plus time s plus 1 to the cube. You take the double derivative basically, and you evaluate s equal to 1. Okay, you can sort of say if I have, let's say, what if I have s is negative 1, negative 1, negative 1, negative 1, negative 1. Let's say I have 5 repeated poles. Okay, so you're gonna have b1 s plus 1 plus b2 s plus 2 plus here is plus 1 to the squared plus b5 over s plus 1 to the fifth, basically, right? So the b1 will be, let's assume I have ys. Okay, they're poles. This is the poles given by this. So my b1 is ys. No, sorry, it should be b5 is ys time s plus 1, and you value at s equal to negative 1, and b4 will be 1 over 1 factorial ys time s plus 1, this might be fifth, sorry, to the fifth, and you take it 1 derivative, and s equal to negative 1, and b3 is 1 over 2 factorial ys time s plus 1 to the fifth. Again, you take a double derivative s again, set to negative 1, and b2 is 1 over 3 factorial ys s plus 1 5 again. Now here I'm going to put a 3 here because you take the derivative, third order derivatives, 3 derivatives is set equal to 1, and b, of course, b1 will be 1 over 4 factorial ys s plus 1 to the fifth to the fourth derivative. Okay, take 4 derivatives, and then you value at s equal to negative 1. Okay, that's how I figure out all those coefficients. So for C1 and C2, you use direct method. Okay, of course you have to use this a, b3 and b2 and b1. Okay, don't assume that we not end. No, you have to use this. You should calculate this value first. It will simplify the computation, right? You can find the C1 and C2. Okay. Then after that, you can use the linear property. Okay, the original function y of s is just be given by the sum of the 5. Basically, it's this guy plus this guy plus this guy plus this guy and plus this guy. Of course, this one is fairly easy to figure out because this is exponential. It's given by a e minus 2 t. This is b1 e minus 1 t. This is t, let's see, I think this one, let me go to the table. So you use the table, try to figure out this one. I think this is a t something. It's b2 et e minus t. Let's go back over here. Figure out how to do it. Okay, e to the t squared, yes. This is a t, e minus t. This is it will be b3 divided by 2 t squared e minus t as well. Okay, this is how we're going to inverse this guy. We have to use follow the video in the inverse Laplace for complex conjugated poles. In the previous video, basically you will have something cosine wt and sine wt. Okay, I think this is 2, w is 2, and you have some e component. Okay, e component. Okay, so you can follow the previous video to figure out the inverse Laplace transform. So basically, I talk about how we figure out this one for the general case. Okay, it's a sort of combination of the 3 different cases I mentioned before.